Hello biologists, this is Miss R and we're going to do the Lab 2.08 Part 1 Lipids and Carbohydrates. Make sure you have the version A of the lab sheet. You may have directions here that look a little bit different. That's okay. They both work just fine. So you're going to want to go to this website here and I'll show you what that looks like. You want to click on the activities here. And then you want to click on Lipids and Carbohydrates, the long version. Make sure you click on the long version. If you can't get the software to wait to load, it's okay. We're going to go over everything. You're going to see everything you need to see right here in this video. So as you go along, we're going to be working on pages in this lab sheet here that correspond to what's in the software. And the software will have a little buttons here that show what page it is, and this is important for knowing what questions correspond to what part of the software. So make sure you're paying attention to these little green bars here and what number is highlighted for each section. I've copied all of the text you need from the software into your worksheet. All right, let's go show you what the that website looks like. So if you're wanting to download the software yourself, make sure you go to this website, you click on Biology Activities, and you want to click on Biology. Then a whole bunch of different activities will occur, and you want to go to Lipids and Carbohydrates, the long version, and just click on this little try button here. And then I'll show you what will pop up. So you're going to see the software pop up. It's going to say it's going to have an index like this. It's going to have some numbers at the top, which will be important to figuring out where you are within the lab. And these are all highlighted as links, and that's where we're going to go. We're just going to click on one of these. If you're having a hard time of getting the software to open, you may need to download the launcher. And that's, if you click on the gray bar, it's the very first one at the top. It's the first option. Don't worry about this bar at the bottom that says user data will not be saved. We're putting it all on our lab sheet, so we don't have to worry about that. So I'm not going to read the introduction to you because you can read it on your lab sheet. It's basically talking about how carbohydrates are a macromolecule. That's basically a big molecule. There's lots of carbon, hydrogen, and oxygen in carbohydrates, and for bigger carbohydrates, things like polysaccharides, like cellulose or chitin or agar, things that we're familiar with in our everyday life. Chitin is on the outside of insects and in mushrooms, and agar, if you've had kind of gelatinous substances that aren't made from animals, that may be agar. We're also going to look at some structure-function relationships, in particular with lipids and carbohydrates. So our big question here is, what do all organic chemical compounds have in common? In varying combinations, the elements carbon, hydrogen, and oxygen and nitrogen make up practically all the chemical compounds in living things. On this page, you'll explore the simplest organic compounds called hydrocarbons. So methane is our simplest hydrocarbon here. You can see it's one carbon, this gray, and then 4 hydrogens. If I move it around here, you can see all 4. 1, 2, 3, 4. I can scroll down a little bit and add another carbon and a couple of hydrogens, and you can see we get a slightly bigger hydrocarbon. Hydrocarbon means hydrogen and carbon, hydrocarbon. I can keep clicking and adding. And you can see that carbon is always making 4 bonds. Here on the end here, it's making 3 bonds with hydrogen and 1 with another carbon. In the middle, it's 2 carbons and 2 hydrogens. In the middle here, also, it's 2 carbons and 2 hydrogens. And in the end, it's 3 hydrogens and 1 carbon. So our first question of the whole lab is, how many bonds does every carbon atom make? Hopefully you figured that out by now. When oxygen is added to hydrocarbons, new properties emerge for these organic compounds. What are the properties? We're going to be looking at polarity, in other words, the negative and positive charges on a particular molecule when you add oxygen. If you create electron-rich areas that become negatively charged, if the opposite poles become electron-poor, they become positively charged because electrons, if there's a lot of electrons, they're negative, so they give an area a negative charge. And if there aren't very many electrons, if there isn't a balance between electrons and protons, it becomes positively charged. Compare the two molecular models that show ethylene and ketene. Here's ethylene and here's ketene. The coloring of the surfaces is determined by the electrostatic potential on them as shown at the right. Here's the kind of charge meter here. You can see that ketene here around the oxygen is very negative because oxygen, we know from when we talked about bonding, oxygen is it's a big pig. It likes to hog the electrons. And so it makes the other side of the electron, or the molecule, makes the other side of the molecule electron poor, so it becomes positive. Ethylene here is all balanced out. There's no oxygen here. So it's a non-polar molecule. So why do you think the charge arranges itself for ketene this way? Why is there a negative and positive end? Why don't you think about it for a second? And let's talk about how polarity affects boiling point. Here's ethylene and ketene again, those molecules that we looked at up here. The dotted lines between the molecules represent the attractive forces between the atoms. So these little dotted lines are how much stickiness or how much attractiveness there are between the molecules. If we're going to adjust the temperature and turn the compound into a gas, basically boil it, which will look like the molecules filling the container instead of clumping together. So let's turn up the temperature here. Let's run this. And it's at a low temperature, so everything is all stuck together. They're not boiling. Let's turn up the temperature a little bit. You can see the molecules start to separate here pretty easily with ethylene, and everything's still stuck together with ketene. Let's turn up the temperature a little bit more. Now ethylene is completely filling up the container, but ketene's pretty much still stuck to itself in a glob. Again, ethylene's filling the container, so ethylene's boiling well before ketene. Let's turn it up a little bit more. Ketene still isn't really boiling, but ethylene is going crazy over here and filling the whole container. All of those molecules are pretty much separate most of the time. And the reason that's happening is because ketene is polar. I'm going to stop this. Ketene has the oxygen here, so this molecule is polar. Let's go back up and look at these molecules. Ketene with the oxygen is very polar, so it likes to stick to each other. The positive ends like to stick to the negative ends of other molecules. You can see that happening below. Ethylene doesn't really care. It doesn't stick to each other as much as ketene. So this requires less energy to separate because it's less sticky to other molecules. This requires more energy to separate because it likes to stick to other molecules anymore. A good analogy maybe is like walking down the sidewalk. That's ethylene. It's pretty easy for you to do that. But walking through sticky, goopy mud takes a lot more energy for you. So which compound boils first? And how does the presence of the oxygen atoms in the molecule account for the difference? So make sure you're thinking about how oxygen is affecting the stickiness here and how that affects the boiling point, the point at which these molecules separate and fill up the whole space. Some molecules dissolve in water, others dissolve in fat. Let's look at what affects the solubility of a molecule. Organic compounds such as fats, steroids, and waxes, which are not water soluble, are soluble in fat. So lipids, fats, steroids, and waxes, they're not soluble in water, but they are soluble in other types of fat. So let's put in a bunch of molecules here. And let's see where they go, where they like to hang out. Let's just seem to get stuck. Okay, so the green one likes to seem to go over to the water. If it's green, it likes to go to water. If it's pink, it looks like it likes to hang out on the fat side. If it's gray, it looks like it doesn't really have a strong preference. It kind of hangs out at the border. So maybe it's half and half. So the greens, they'll head over here, and then they'll just head right back to water. So which do you think the following are true? The pink molecules love fat. The green molecules are loving the water. Part of the gray molecules loves water and part hates it. Or D, none of the above is correct. You decide. Look at those pink molecules. Where are they? Look at the green molecules. Where are they? And where are those gray molecules? They're hanging right out at the boundary here. Now let's see what happens if we have a lipid and it's just hanging out in water. So notice that the lipid hangs out with itself and the water's hanging out with other water molecules. Now if we change this lipid and we put it in fat, it doesn't hang out with itself anymore. It'll go hang out with the other fat molecules. So let's think about, and I'm going to put it back to water. Hydrophilic means something is attracted to water. Certainly doesn't look like this lipid here is attracted to water. And hydrophobic means something is excluded from water because water is more attracted to other water molecules. That certainly looks like that's happening right here. The water is more attracted to the water, and so it kind of shoves the lipid all together. Are the lipids shown here hydrophobic or hydrophilic? Please explain your answer. And I'm going to flip back and forth between the solvents here. In fat, this lipid here is spreading out. It's interacting with the other fat molecules. In water, it's not interacting with the water. It gets shoved together with the other molecules and just interacts with its other lipid molecules because apparently the water would rather hang out with other water molecules. So now you have enough information to answer this question. We're going to page 5 now. Lipids are broadly defined as any molecule that can dissolve in fat. Do all lipids have the same properties? On the next few pages, we'll explore models to help us answer this question. Janus in Roman mythology is a two-faced deity, one for enemies and one for friends. When scientists examined a more complex lipid type called fatty acid, they found similarity to the two-faced deity, or to Janus. Fatty acids are long chains of carbon and hydrogen atoms, just like the hydrocarbons on the previous pages. Here's a fatty acid, and here's a hydrocarbon. The big difference here is the carboxyl group. And a carboxyl group, remember, is oxygen bonded to, two oxygens bonded to a carbon. The hydrocarbon and the carboxyl group are like the two faces of Janus. They face opposite directions and interact with two different types of other molecules, polar and nonpolar. This would be the polar part, or the charged part of the fatty acid, and this is the nonpolar part. So I'll show you what's underneath that charge map here. We can make it translucent here. You notice this is not charged, there's no charge here, and there's no oxygen. Here, when we add a carboxyl group, we add some oxygen, we get some charge happening on this fatty acid. So let's play the movie for this one. The carboxyl group is the head group of this fatty acid. Here it's highlighted in yellow. The carboxyl group has two electron-greedy oxygen atoms, so they're hogging the electrons. What can you tell about the properties of the fatty acid from observing it? So hopefully you can look at this fatty acid here and think about how it might behave if you stuck it in water. Compare the structure and polarity of the fatty acid to the hydrocarbon. So here's the hydrocarbon, here's the fatty acid. They're pretty similar until you get to about right here. Then you add oxygen, things get polarized, and they become different. So make sure you include oxygen in your answer. What happens when you add oxygen? What does the carboxyl group do to the charge? That can help you answer that question. Remember, if you're polar, if you're charged, water likes you. So this part of the molecule, the head, is probably going to like water. If you're not charged, like we saw in the lipids on the previous page where they're bouncing around, where these guys were bouncing around in water, these are not charged. So they're just going to like stick to themselves. They're not going to like water. They do like fat. That's an uncharged molecule. It's not a fatty acid. Oops, skipped over to. So the tail here is not charged, so it's not going to like water. All right. Fatty acids at the water-oil interface. So we've simplified the fatty acid here. Here's the carboxyl group. The tail, the hydrophobic tail, is going to be represented as a squiggle. And the head, the polar head, the head that likes water, is going to be represented as the green head here. So we're going to kind of play with the fatty acids here a little bit. So you're going to see over time what happens if we just let the model run. The head's going to end up in the water, and the tail's going to end up over in the oil. This is an oil-water interface. Think of like salad dressing. And even if we pull this, even if we pull them up, let me stop here and pull them up, pull them into a different place, eventually they're just going to find their way back so that the head's in the water and the tail's in the oil. Because there's a polar head here that's hydrophilic, it likes water, and there's a hydrophobic nonpolar tail. So we just talked about why the tails are located in the oil and the heads in the water. The heads, remember, are polar or hydrophilic. Polar molecules, molecules with a charge, like to be in water because water is charged. Water is a polar molecule. The tail here doesn't have any oxygen in it, so it's nonpolar and likes to be in a nonpolar fluid like lipid. Why are fatty acids compared to the two-faced deity Janus? Well, think about what they're doing here. There's kind of two parts of them, the polar part and the nonpolar part. So you have enough information to answer these two questions. And you can answer them on your lab sheet. So my cells here, where you have a bunch of fatty acids, they have a polar head here, and they have a nonpolar tail. And this is what happens when they're in water. So I have water clicked right now. The polar heads are facing out towards the water. The polar heads interact with water, which is another polar molecule. The nonpolar tails here face in. They don't want to interact with water because they're nonpolar. Water would rather interact with itself than interact with the nonpolar part of the fatty acid molecule. Now I'm going to stop this. I'm going to put it in oil. I'm going to change the solvent and we'll see what happens. Things break up and watch the molecules actually flip around. When they're in oil, which is nonpolar, very different from water, the heads face in and the tails face out. The tails now can interact with a like solvent, a nonpolar solvent, and those polar heads are like, get me out of here. I don't want to interact with this nonpolar oil, so they all group up in the middle. So let's talk about soup now, which seems really odd, but have you ever observed beads of oil on the surface of soup? Or maybe you've had salad dressing where you have water and oil together. Explain how this model, the micelle model above, can explain the occurrence of those beads or water and oil not mixing. I will let you think about that one. Does the nonpolar lipid, like salad dressing, like oil in salad dressing, want to interact with polar water? So now we're going to talk about what structures can be produced when we place phospholipids in water. So we have a stearic acid, this is fatty acid, and when we hook up a couple fatty acids together, we get a phospholipid, and you can see there's a phosphorus in there as well. Scientists think that the first steps of cellular evolution was the emergence of small spherical particles made of lipids. Gradually, these lipids became more complicated. Cell membranes formed that were capable of separating the interior of the spheres from the water outside. The models on this page will help you explore how cell surfaces may have evolved. So let's learn about phospholipids. Here's a nifty picture of a phospholipid. You can see the polar heads, the oxygen head, and the nonpolar tails. These are the nonpolar tails. These are the nonpolar tails, the yellow here. They're forming a bilayer, so there's one on the outside of the cell and one on the inside of the cell. And they're separating what's on the outside of the cell to what's on the inside of the cell. So we're going to run this model, and we're going to see that these little tiny molecules can cross the cell barrier. They're sneaking their way through. Because they're small enough and they're not charged, they can kind of scoot through here. But if we try to get larger molecules across there, things are not going to work so well. Larger molecules and ions cannot pass through the cell membrane unless we do a pore. This is a special protein that's embedded in the cell membrane that helps these larger molecules cross, and it can also help ions cross as well, but that would be an ion pump, and we'll talk about that later in this next semester. So, which statement about membrane phospholipids is not true? Well, let's review here. There's a bilayer, in other words, there's two layers here of phospholipids. These are the hydrophobic tails. These are the hydrophilic heads. They are allowing small materials, if we do this, tiny little materials that aren't charged can pass through them. And they are not moving from side to side. They're not flipping from side to side of the membrane. What would happen if the cell membrane burst? Well, think about it. Okay, you've got a bag of, let's say, soup, which is kind of like a cell. Cells have kind of chunks in them, and they have some liquid in them. If your bag of soup gets a hole in it, what's going to happen? Are you going to have a bag of soup anymore? All the stuff that's supposed to be inside the bag is probably going to get outside the bag, and what you're trying to keep outside of the bag, maybe you're trying to keep air out or bacteria out, that's going to get inside. So let's compare lipids and carbohydrates. Imagine adding 15 teaspoons of sugar to a 12-ounce glass of water. When it dissolves, you've got the same amount of sugar as a can of soda. But what if we try to dissolve even a single teaspoon of oil in water? It floats to the top and doesn't dissolve. Why is there such a big difference here? Carbohydrates are familiar to us. Starches, sugars, like lipids, they're made of carbon, hydrogen, and oxygen. But carbohydrates have very different properties. Why? Well, let's look at the surface displays here. It's a little bit charged here, the lipid, the fatty acid over here. But look at this. Glucose is lighting up like a 4th of July parade. There's positives and there's negatives. Where there's an oxygen, there's some negative blue stuff going on here. So this is all kinds of charged. This is a little bit charged on one end. So more oxygen is kind of making there some craziness with the charge. So when we look at glucose here, we can see that there are 1, 2, 3, 4, 5, 6 carbons, and there are 1, 2, 3, 4, 5, 6 oxygens, and there are equal amount of carbon and oxygen, and there's twice as many hydrogens. If we count the hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there's one we can't see, 12. So there's twice as many hydrogens as there is carbon and twice as many hydrogens as there is oxygen. And if we look at, let's look at charge again. If we look at how oxygen affects charge, we can see very clearly here that if you've got more oxygen, you've got more charge. There's only a little bit of oxygen here on this end, and that's the only part that's charged. So basically in hydrocarbons, if you've got oxygen, Wherever that oxygen is going to be the most polar part of the molecule in most cases. We're going to scroll down now on the same page and compare the solubility of sugars and hydrocarbons. Carbohydrates are an important source of energy. Hydrocarbons are petroleum products and contain abundant energy, but hydrocarbons don't mix with water, and since we're mostly consistent of water, we don't use hydrocarbons as a source of energy. Carbohydrates evolved as a better energy source for living things. The generic formula for carbohydrates is CnH2nOn, like C6H12O6. The formula makes it appear as if it may consist of a carbon portion and a water hydrate portion. Sugars have as many oxygen atoms as carbon atoms. We talked about this a few minutes ago. This abundance of oxygen makes sugars highly polar because oxygen is very electronegative and highly water soluble. If it were not for water in our blood, our cells, our favorite breakfast drink, might be gasoline, not milk. Gross. So we're going to compare how glucose, a carbohydrate, and benzene, a hydrocarbon, dissolve in water. They have similar ring-like structures and a similar number of carbon atoms. So let's run. This is benzenes with water, and we're going to remove the barrier. Here's the water, these hydrogen and oxygen deals. And we're going to see how they interact with benzene, which is a hydrocarbon, no oxygen. Just hydrogen and carbon. Benzene isn't really interacting so much. Let's reset here. And let's click glucose. Remember, glucose is going to have oxygen in it. So it's a carbohydrate. And we'll run that. Withdraw the barrier. And right away we can see that all that oxygen is starting to interact. The oxygen in the carbohydrate, the oxygen in the glucose is starting to interact with the polar water. Those polar oxygen molecules are starting to interact with the polar water. So, explain how the presence of the 6 OH groups affects the solubility and properties of glucose. Well, this would dissolve in water because water is surrounding it, and it would pull the molecules apart. Glucose molecules that are all stuck together in a big chunk of glucose would get pulled apart and dissolve in water quite easily. Unlike the benzene molecules, which really pretty much kept to themselves and didn't interact with the water at all. And so benzene would not dissolve in water. All right, let's go to page 8. So many large carbohydrate molecules can be made by joining together sugars. Such compounds are known as polysaccharides. They can form certain structures that affect the function of carbohydrates. So let's do movie 1. Let's build a polysaccharide chain. Polysaccharides, like cellulose, agar, and chitin, are important building materials for living creatures. All walls of higher plants are made of cellulose. Some walls of algae are made of similar polysaccharides called agar. External skeletons of crustaceans and insects are made of chitin. So I believe this is cellulose. And when cellulose lines up together, those long, stringy cellulose molecules make really a lot of hydrogen bonds, and they're really tough to make, tough to break. Because you get long, stringy molecules like this making hydrogen bonds right here, and so they're not only fit together well, but they also are hydrogen bonded, so they make this tough, stringy, fibrous stuff that you get in a lot of plants. If you want space fill, that's what it would look like, or if you just want surface, it's kind of what the surface would look like. Cellulose is made of long polysaccharide chains. That line up in parallel. How does this structure relate to its function? Well, here you go. Here are two long cellulose molecules. They're bonding to each other, and the long, stringy molecule is really good at making long, stringy fibers inside plants. Think of like celery, or when you like tear a green branch apart. It's pretty stringy. So when we get more hydrogen bonds, when we have long, stringy molecules and we try to pull them apart here, let's click the run button here. So click the run button, click the mouse and drag the mouse down. You should see an arrow appear on molecules. Click the A on the keyboard while holding the mouse until it separates. Okay, let's do that. This is really hard. I'm working really hard to try to separate these two molecules. And because of all that hydrogen bonding, it's not really working. I can't even get them apart. I did manage to do it and took a screenshot on your worksheet so you can check that out. So let's think about how long linear polysaccharides make strong fibers. They are lined up together, and then it's those hydrogen bonds. They fit well together, but then it's also the hydrogen bonds between those two long stringy molecules that are really important. You can see the little hydrogen bonding here, the little fuzzy stuff. Oh, I see. I have to up my strength here. It's like a video game. But if I'm like at weak strength, I can't pull these apart. Let's push them back together. It's pretty hard until I turn my strength up like, more than halfway. I can't get them apart. If I'm down here at weak strength, you can see in the lower right hand corner there's a little bar here. It doesn't work at all. It's really hard to rip these two molecules apart because of those hydrogen, but they fit well together and they have hydrogen bonds. So polysaccharides can be distinguished by the amount of branching that occurs. Linear starches tend to form hydrogen bonds between chains. How does branching relate to the function of those starches? In the model, we're going to click a run and use the slider to change the temperature. We can compare the strength of attraction between the linear polymers in the fiber, such as cellulose, that's the ones over here, and the more branched chains over here. So let's try to rip these apart here. Let's turn up the temperature a little bit more. Nothing really happens to cellulose, which makes sense. Have you ever tried to boil sawdust? It really doesn't do anything. It stays sawdust. But the starch over here is coming all apart. It'll get a little hotter. Starch is not sticking together anymore. Which makes sense, because when you boil things that are starchy, like noodles, the starch dissolves into the water. You don't dissolve your sawdust, which is a lot of cellulose, but you can dissolve starch. So think about why you can separate branched polysaccharides up here. They're not stuck together in the same way these linear molecules stick together that are all packed together. If you have something all branched, it doesn't quite line up the same way and it's easier to separate. Okay, let's talk about the differences between starch and glycogen. Glycogen is a polysaccharide of glucose that functions as the primary short-term energy storage in animal cells. And think about why glycogen might be different than starch, which comes from plants. Because plants don't have to run away, but animals might have to. Glycogen is similar in structure to starch, but glycogen has far more branches. Why? The model below shows how every branch of glycogen and starch are attacked by special enzymes, glycogen phosphorylase, that cut the end glucose molecule from the branch. In which one would more glucose be released in the same amount of time? Plants cannot jump and don't need the rapid release of glucose for energy as animals do. So let's look at these two different models here. So starch is in plants, which don't have to jump and run away. Glycogen is in animals, which do have to